I'm going to talk about a novel development in RPKI land, something I like to call the ERIK Synchronization Protocol. My name is Snijders. I like tinkering with systems that form the global internet. Yeah, let's dive into it. So as you might know, the internet is glued together using a protocol called BGP, Border Gateway Protocol. In essence, in BGP, we pass around messages about what's located where, but these messages are not authenticated. So a second system was designed called the RPKI, Resource Public Key Infrastructure, and that component is cryptographically secured. And it is the union of these two systems, BGP and RPKI, that dictates how routing happens in the modern age. Now, to make use of RPKI, the data needs to be distributed, obviously. You cannot make use of something that's not in your possession yet. And research has shown that it takes 10 to 60 minutes to distribute or revoke new ROAs. ROAs are the digital objects that encode what ASNs can originate what IP space, and they are one of the cornerstones of routing security. So 10 to 60 minutes is a really long time, especially if you messed up the ROA configuration. The letters are really close to each other, and you inputted the wrong ASN, and you wiped yourself off the internet. You know, and now you're waiting for the 60 minutes to pass. It's really tedious. It's like watching paint dry. Your boss is screaming, "Why are we down?" And you're trying to explain that there is a delay in RPKI, and this is annoying. So, what is it we're going to do about this problem? Because 60 minutes is not acceptable. I want stuff to go way, way faster. This stuff needs to propagate in less than 5 minutes, maybe even less than that. How are we going to achieve this? A high-level overview of how the RPKI supply chain functions. I'm skipping over a lot of not-so-interesting details. But on the right side, we have the RPKI repositories. The data gets into those repositories through RIPE NCC's web portal or APIs. There's a number of ways to do that. These repositories make the data available through two protocols, rsync and RRDP. Then we have validators. Validators are software packages that run inside ISP networks, and they fetch data from these repositories. They do cryptographic verification, and then spit out a sort of plain text variant of the information towards the routers, and then the routers make decisions based on the information they receive from the validators. All right, cool. Beautiful overview. But the reality is that there's a lot of delay factors in all of this. That 10 to 60 minute story, there's a lot of parameters that contribute to these delays. You have to imagine that as Dutch ISP, you install your validators, cool. These validators now need to connect to things on the internet that are not close by. So for instance, the Japanese RPKI repository is hosted in Japan, and that means there is a lot of latency on the back and forth between the validator and that particular repository. Afrinic is hosting a lot of their stuff in Cape Town. Aaron hosts their repositories in the United States. And validators do not have a choice in where they fetch the data in the current form of the technology stack. So this is why I say things actually are single source. Yes, there's many repositories where you fetch data, but there's no overlap between the repositories. It's not like I can go to the RIPE repository to get the ARIN data. I need to go to the ARIN repository to get the ARIN data. So single source might be an issue. Some repository operators do a splendid job, like RIPE NCC. You know, they use a CDN to distribute the data. Hi, Akamai. They also use Cloudflare, I believe. You know, it works well. But the Indonesian repository does not use a CDN, and that might be a slowdown. These repositories might be hosted behind links that are congested. So there's packet loss on the connection, and that means that validators have to retry. Validators themselves use different timers. Some validators will poll every 10 minutes, some will poll every 50 minutes. And then there is the matter of the efficiency of the synchronization protocols themselves. And that's what we're going to talk about today. To latch on to yesterday's theme, Joe, why not just use the cloud? Clearly, distributing data on a global scale is a problem that has been solved by the likes of Dropbox. This is true for some sets of data, but the RPKI data set is really challenging. At this point in time, RPKI data is roughly 500,000 files, of which 250,000-ish change once or more times a day. The total size is not that impressive, and there's, at this point in time, roughly 5,000 endpoints that fetch the data. So you might think, you know, we can distribute Fortnite updates quite easily. But the issue with RPKI is it's so many separate files, and we want it to be really, really fast. But it also needs to be cheap, because maybe the repository is hosted on a super fast server, but what if the validator is behind a satellite link? And here in the Netherlands, we are blessed with super fast internet. Thank you, KPN. But you know, that's not the case everywhere on this planet. There are locations on the internet where things just are slow. And those locations also need RPKI data. And another issue is RPKI is growing. So today it's 500,000, but maybe 2 years from now it's 1 million. Like, RPKI is becoming more and more popular, and that has consequences in the size of the database. So Dropbox is not going to help us in this instance. What is used today to distribute RPKI data? We have two protocols. One is called rsync. Yes, the Unix utility that many of us have used for the last few decades. And one is a protocol specifically designed for RPKI called RRDP, RPKI Repository Delta Protocol. We've all heard great stories about rsync. rsync is marketed as a very efficient copy tool. And it is. But also, it is not really in the use case of the RPKI. rsync is considered efficient because ultimately, in the programs, in the protocol execution, you end up transferring the difference between what you already have locally and what the remote site has to offer. That's super cool. But what is challenging is that figuring out what exactly is the difference between what I have locally and what the remote site has also consumes CPU, cycles, and bandwidth. So to put this in perspective, just to figure out whether I am synchronized with the remote servers or not already costs 4 megabytes of network traffic without actually transferring anything. So you have the server and the client, and they go like, hey, hello, do you have some data? Sure, I have this available. And then they exchange 4 megabytes, and then the client is like, oh, You know what? We are already synchronized. Sorry for bothering you. It's really, really expensive to do rsync synchronization. If you run rsync, if you run the validator at a 15-minute interval, rsync ends up consuming roughly 40 megabytes per execution of the interval. So that's roughly 160 megabytes per hour. And if you're on satellite or, before we had European-wide roaming rules, that would be a really expensive joke to synchronize. If you run rsync every 60 minutes, it costs 52 megabytes, median measurements. So you might wonder, why is this not linear? But we'll get into that. Then, surely, we have improvements in this newer protocol called RRDP. RRDP, in a nutshell, it is a HTTP-based protocol where the binary RPKI data is encoded using base 64, and then it's put in an XML document, and then the XML document is made available through a web service. It can be hosted behind CDNs. And the essence of RRDP is that the publication point writes into a sort of journal things that change. So it will write into the journal, this file was added, or this file was removed, or this thing was updated. So instead of exchanging the full file list of what's on the remote side and comparing that with what's locally available, like you do in rsync, you're not exchanging a giant list of files, but you're exchanging the modifications to the data set. Validators download this journal, they replay the events in the journal, and that's how they arrive at the current state of events. The challenge here is that in RRDP, if you want to read today's newspaper, they forcefully make you download yesterday's newspaper as well. That's sort of the analogy. So if you create a ROA every 10 minutes, but you're synchronizing once an hour, every validator that follows that timing pattern will have to also download those 5 previous states at the 10-minute marks on the clock and then basically throw them away. So a lot of data that's downloaded in RRDP is outdated by the time you're downloading it, and that's a waste of bandwidth. So measuring RRDP, it's in the minimum case, just figuring out, am I synchronized or not? For the average RP deployment, RP is a validator, it's quite cheap. You spend a few hundred kilobytes to figure out, am I synchronized, yes or no? If you run RRDP every 15 minutes, it consumes roughly 5 megabytes. If you run it every 60 minutes, it consumes 100 megabytes. So what we're faced with is this weird trade-off that if you do synchronization very often, RRDP wins, but if you're synchronizing less often, rsync wins. And the issue here is that both protocols are not truly optimal for the task at hand. Rsync is really nice in low bandwidth environments. On high latency links, it suffers a bit, but if there's congestion, rsync has a sort of resume functionality. It performs better than RRDP. On the downside is that it's quite easy to bother rsync servers and send them specific instructions to waste their CPU cycles. On the flip side, RRDP servers can DOS the clients because the RRDP server sort of offloads all computational tasks to the clients, and one of the consequences is that there could be disproportional disk space usage. RRDP does not really have a resume function, so if there's any interruption to the synchronization effort, the whole thing needs to restart from scratch, and that could mean re-downloading hundreds of megabytes of data that you already have locally stored, but the protocol doesn't allow you to sort of skip over the intermediate steps in the journal. This, in turn, because you need to do a full download if something goes wrong, can cause a thundering hurt, which in turn can be result in unavailability of the repositories. And with everything I've mentioned so far, what it boils down to is that slow servers, slow for whatever reason, have impact on some parts of the system and drag the slowness is problematic if you consider the expedient delivery of ROAS important. Now, as with all technology standards, when there's a problem, you just make a new technology, and this time, for sure, we're going to get it right. And with that, I want to introduce a proposal, the ERIK Synchronization Protocol. In the ERIK Synchronization Protocol, I've taken concepts, some of which are more than 50 years old, and glued them together into a new cocktail where I think that it will make RPKI data distribution perform really well. Instead of a journal, instead of a list of files, Merkle trees are used to help clients understand which parts of the tree are not yet in sync. And then because content addressable file naming is used, they can fetch exactly the missing pieces instead of trying to compute on the fly what pieces are missing. The RPKI has other interesting properties in that a lot of the components have linear growth counters that we can use to reliably assess, is this old or new information? Should I fetch the thing, or do I already have a newer thing and I don't need to fetch the thing? And then all of this is transported over HTTP because that's favored by many operational teams, and it allows easy use of CDNs. The protocol is, of course, named after our good friend ERIK Protocol, who passed away last year. Now, the architecture of how I envision we can deploy this protocol, in essence, it's the injection of a new caching layer that is driven by the operators of validators. Because, as I mentioned before, RIPE-NCC does a great job of offering a globally distributed, anycasted infrastructure to distribute the data. This means that access to RIPE data everywhere on the planet is pretty fast. But the repositories that do not use a CDN and are hosted only in a specific geographical location, like only in Indonesia or only in Japan, they might not be using a CDN, and we cannot force them to use a CDN. You cannot. It's the same with authoritative DNS servers. You can recommend people like, hey, you're running an authoritative DNS server, you should make it super available. And then the owner of that server is like, well, I don't have money for that, or time, or I don't care. And there's not much you can do to compel people to run globally distributed infrastructure. But with the ERIK protocol, the ERIK cache servers slurp in data via rsync, via RDP, via any means necessary, and make that available to clients. And the clients, the validators, can pick and choose which caches they fetch data from. So this is a means to CDNify the entire RPKI, whether the origin was CDNified or not. So this caching layer, I think it is going to be an interesting experiment in distributing data in a more efficient way. So instead of that round trip from Amsterdam to Japan all the time, the long round trip is to the ERIK server, and then ERIK servers can be distributed all across the globe and will be close to all validators. So some advantages of how the ERIK protocol differs from rsync and RRDP. Just like in rsync, clients jump to the latest state. You only want today's newspaper. You don't care about yesterday's news. So the ERIK protocol has that property that you skip the intermediate states and you just jump to the final outcome. In the ERIK protocol, you only download what actually changed. So you're not downloading historic, by now irrelevant data. You just download exactly what is needed in this moment. And just like in RDP, and this is considered a very attractive property of RDP, that the data is static data that you just host on a web server. There is no database queries on the back end to make it work. Just like RDP, the data is all static, pre-calculated, and this makes distribution way easier. HTTP-based, it is very light on state. So a client can talk to multiple different ERIK servers that are operated by different entities. So, RIPE NCC could operate an ERIK server, AMS-IX could operate an ERIK server, I could operate one, and then clients can just round robin between those servers to fetch the data. And this is very unlike RDP, where you follow a very specific journal and there is no mirroring possible to other places in RDP. It is easy to combine with existing protocols. So we can go to a model where I can say, well, in the next RPKI client release, 10% of requests is going to go to an ERIK server, 90% of requests, as sort of a safety mechanism, is going to the original servers. And then as time goes by, we can maybe skew how much data you're fetching via what protocol. In other words, I would argue ERIK protocol is cheap, fast, and efficient. It's all free. And I can prove it, because I've done some measurements. The last few nights I was coding on my laptop to quickly produce an implementation to be able to measure whether anything I would say today is actually true. But, I met the deadline, and last night I produced some data. Before we discussed rsync, just to figure out whether we're synchronized or not, whether there is any data to transfer or not, that takes 4 megabytes. In RDP, using HTTP semantics like if modified since and the initial entry point being tinier data, that exchange is much smaller. And in a similar fashion, in the ERIK protocol, it's just a few hundred kilobytes to figure out, am I in sync or not? If you synchronize every 15 minutes, in rsync, it was expensive. It's 40 megabytes per run. In RDP, it's fairly cheap. It's 5 megabytes. But in ERIK, it's even cheaper because you're only synchronizing what is currently relevant. You're not synchronizing the historic data. And then if you look at the deployment scenario of synchronizing every 60 minutes, ERIK is cheaper than the other two options because it doesn't have the overhead of rsync and it doesn't have the historic data like RDP. So this is super promising, but more research is needed to see if these numbers hold up in practice and at scale. But yeah, this is cause for celebration that we might be on a path that is useful. And in these experiments, the outcome of the validator in all scenarios is the same. So what the routers receive is the same set of data, same set of ROAS. There is no loss of fidelity or loss of detail in these transportation mechanisms. This is the data spent to accomplish the same outcome. The to-do list. It starts with writing a document that explains how the protocol works and trying to encourage people to write an implementation and give feedback on the documents. There's a bit of a cycle between writing the document, writing software, doing measurements, going back to changing the document, changing your software, doing measurements. There's a lot of intricacies in protocols like ERIK. There are parameters that you can tune. and I won't go into the technical details, but without changing the on-the-wire format, but like changing how you pack data together, there might be efficiency wins. So the final form of this protocol is not yet known. It's an interesting space to explore. I expect this cycle to go on for another 2, maybe even 3 years, which means that probably 3 or 4 years from now, a large portion of RPKI data, if the ERIK protocol turns out to be successful, will be distributed using that protocol. So stay tuned. My penultimate slide. How can you help? You can sponsor me. I'm currently jobless. It's a great pun. If you pay for food, that's great. Then I work on protocols like these. You can also sponsor your time. So you can take a look at the draft specification, which is really in rough form. But if you're interested in how a technology develops from like start to finish, what that entire process is, what it would mean to be involved in an IETF working group, this is a chance to latch on, because this is the very beginnings of a new protocol. Like this idea is just a few weeks old. So if you want to see a protocol development from start to end, this is your chance. And I need computational resources to run experimental ERIK servers and do measurements of what it would mean to fetch data via ERIK protocol in comparison to rsync, in comparison to RDP. So if you have an unlimited cloud account that you can share with me, that's nice. Shout out to Amazon and DigitalOcean. They are already chipping in with resources, but I think it's really good to not have a dependency on a single cloud and use multiple suppliers of resources. So this is why I'm putting out the request for help. And with that, I would like to solicit feedback, questions, commentary.
Ladies and gentlemen, are there any questions? Well, at least the applause is there already. I see one question. Of course, it's Stavros. Stavros from AMS-IX, ladies and gentlemen. Stavros, please stand up.
Shall I state name and affiliation?
No, we know you, but
I think it's useless. We know you very well. Thanks, very interesting. Looking forward, and I liked also the table with the results and the comparison. So that was nice that you managed to bring it just on time for the presentation. Yeah, putting a cache in front of a routinate or RPK client, which is also a cache, sounds like a bit. I still feel like that we have adopted an RTM before to be able to provide ROAS. That would be a better approach compared to RDP and rsync, because an RTM4 also has the versioning inside the Delta files, which means that we know very quickly if we are up to speed or if we are not in sync. And we can also go back a little bit back to see how many details we lost, but we don't need to bring all the data. And also an RTM4 takes cloud distribution into consideration, which means that we can also have the data via cloud providers distributed, which actually you try to achieve as well with this ERIK synchronization protocol. So would it be a bit better or more quick to adopt or adjust an RTMv4 in order to achieve the same result?
That's a super fun question. Full disclosure, Stavros and I have been working on the NRTM version 4 protocol in the last, what is it, two years?
2.5.
Yeah, long, yeah. NRTM is near real-time mirroring protocol. And it is used to mirror IRR databases. IRR databases, Internet Routing Registries, are a predecessor of the RPKI. So IRR is plain text data blobs with no cryptographic signage. RPKI is a binary format with cryptography involved. NRTM is a general purpose synchronization protocol in the sense that you can pack any kind of data inside this protocol and transfer it. And this general purpose property is useful because IR data is opaque blobs, and the computers involved might not exactly know what it is they're transporting. So on the one hand, it is flexible, but on the other hand, just like rsync and just like RDP, I think that the general purpose characteristic means it is not optimized specifically for RPKI data. And the ERIK protocol, part of the signaling between the server and the client is the RPKI data itself that the client will need in the future. So what this means, imagine you have a few files that contain lists of other files. Not the files themselves, but it's like you have a bunch of files that are a list of files. Then you make a list of those files. So there's now a level of indirection. And this is how rsync and RDP and NRTM essentially work, is that you put whatever you wanted to transport inside an envelope, and that's what you pass on. But instead of using an envelope to put in a payload and distribute that, what we're doing in the ERIK protocol is more like postcards, where the envelope and the payload are the same thing. So now we're no longer distributing the weight of the envelope, but we're distributing the payload, and the payload itself is used to signal what else is needed to be synchronized in the protocol. So long story short, I think that my guess would be that NRTM version 4 would be somewhere between rsync and RDP in terms of data consumption, which is not bad, but I'm like, I want to explore the maximum optimized version of how to transport this data. And this is why I arrived at a protocol that really is only useful for RPKI data and nothing else. So there was a bit of a monologue to answer the question.
I see another question there in the corner. Daniel, also from AMS-IX. You don't have to be AMS-IX personnel to ask questions, just so you know.
Yeah, I think everyone left already, other than AMS-IX. So, okay, the question really is, so you build a caching layer, right? Then the previous problem was you have a lot of endpoints that you take things to the validator to validate. What if the caching layer grows to the same 500,000? Isn't that just moving the problem one level up?
Yeah. It's like a hot potato, and you just throw it around, and yeah. So introducing a caching layer is always a bit challenging. Sometimes there's complexity involved. What if your caching layer is out of date and whatnot? But as an interesting property of the ERIK protocol is that if one cache is dysfunctional, out of date or slow, you just use a different one. So I think the future will be that validators can pre-configure it with 5 or 6 cache servers that they approach, and through heuristics they can sort of latch on to the one that is producing good results consistently, and maybe ignore one that's already always outdated or a bit slow. But there is some complexity involved in using an additional caching layer. Now, another consideration, the likes of RIPE-NCC already today host RDP servers that are burning through bandwidth like there is no tomorrow. So there is an actual business case for RIPE-NCC to operate an ERIK cache server, because the ERIK cache server will distribute more data or more valuable payloads for less bandwidth, and that reduces the pressure on their RDP server. So I think that in looking at incentives to see how this protocol can be deployed in the wild, we shouldn't really think of this as a random entity is going to run a cache and your validator has to connect to the thing, because then we're repeating the issue like we had with RDP. I think the big players in the ecosystem that already run RDP servers will be compelled by the attractiveness of this protocol to set up secondary caches that are just more efficient to retrieve to distribute the data. And I trust that the likes of RIPE-NCC and Erin and APNIC, they are competent to run RDP servers today. They will also be competent and be able to be trusted to run ERIK servers in the future. Running a cache server is not going to be for everybody. There is trickery involved. There is operational complexity. But I think that the cost of running those servers will roll up to the entities that benefit the most from operating these servers. So I think this will be, to some degree, self-stabilizing.
Okay. We're going to do one last question. One last one. Alexei, our previous presenter.
So I'll go back to where you were. So I'll try to
it's on the floor, right? Or
a bit lighter. So on this slide, you claim that it is efficient, fast, and cheap. But in school, I was always taught that you have to choose two of those. So what are you not telling us?
I honestly think that it is efficient, fast, and cheap. Like it consumes less bandwidth, so it's cheaper. It's fast because you skip over data that's no longer relevant. It's efficient. You fetch just what you need, nothing else. And there will be downsides. I just don't know exactly what they will be. I mean, on paper, this protocol looks good. Initial measurements are promising. And this means it's time to bring it to a wider audience and conduct larger scale experiments that will last multiple months and see, like, is this really as good as we hope it is? And there's going to be gotchas. But we've been through the cycle with rsync, and I've written an RFC that explained how to maximally optimize an rsync deployment for the RPKI by fiddling with timestamps of the files. And so I feel like, okay, rsync, we now have 15 years of operational experience. We have made it as efficient as is theoretically possible in the protocol. With RDP, we've gone through a similar cycle. The first version and what it is now, there have been tweaks along the way. The security issues got patched. We now recognize, like, oh, you got to turn on HTTP compression to... So, you know, we learn and iterate. And the ERIK protocol, the same cycle will happen. Like, initial results, cool, but we have to go through a cycle and carefully monitor and experiment with what makes it strong and robust, but what are the weaknesses, and how can we mitigate weaknesses associated with this protocol. So that is just part of protocol development.
Not that it matters much, but have you compared memory footprints yet?
I have not. No. But I'm optimistic. Like, rsync is heavy on memory. RDP and ERIK are static content, so it's on server and client side, there's not much memory usage, I think. But.
Okay.
All right.
And we're out of time. Thank you very much, Job.
Thank you all.
Ladies and gentlemen, Job Snijders.